I want to start by doing a little recap of what we did in the last class. So in the last class, we had discussed the discrete Fourier transform, which we said is a discrete transform of a discrete time signal. And the difference in one of the key differences in this DFT and the discrete time Fourier transform of DTFT is that one is discrete, the other is continuous, and the other difference is that discrete Fourier transform, at least for the sake of this class, we are only going to define it for finite duration signals. So we talked about how do you define the length of a signal. We talked about the concepts of zero padding. So we said that the discrete Fourier transform endpoint DFT of a signal of length less than or equal to n, it is given by x of k equal to summation n from 0 to n minus 1 xn e to the minus j 2 pi k over n times n. And this we said can also be written as wnkn. And the inverse discrete Fourier transform is very similar. It's 1 over n summation k from 0 to n minus 1 x of k wn minus kn. So this is k goes from 0 to n minus 1, and what you recover also goes from n equal to 0 up to n minus 1. We did a few examples of that, and then where we ended was we said that discrete Fourier transform helps us learn about the discrete time Fourier transform of discrete sequences. So they are intimately related, and the way we saw that was we said the DTFT of xn, if it is finite duration, is given by n equal to 0 to n minus 1 xn e to the minus j omega n. So this is x of e to the j omega, and when we compared the expressions of x of k, we saw that all that is different is that little omega in discrete time Fourier transform is replaced by 2 pi k over n. So what we learned was that the kth sample of the discrete Fourier transform is nothing but a sample of the discrete time Fourier transform at little omega equal to 2 pi k over n. So we said as k goes from 0 to n minus 1, this means that we are sampling omega goes from 0, so 2 pi 0 over n, that's 0 to 2 pi minus 2 pi over n. So it's like we are sampling the little omega axis from 0 to 2 pi. Okay? So DFT samples the DTFT from little omega equal to 0 to little omega equal to 2 pi minus 2 pi over n. And from this, what we concluded was that the distance between two samples of DFT, so that is equal to 2 pi over n. In 0 to 2 pi, it gets divided into n bins, each of size n, which means that as n gets large, we are sampling the little omega axis denser and denser. So what this means is that DFT, even though we can't really recover the entire DTFT because that will require us to process the signal for every little value of omega, every little omega from 0 to 2 pi, what we can do is sample these values at multiples of 2 pi over n, and that is what the DFT provides us, samples of the DTFT from 0 to 2 pi, and as our as our capital N increases, as the number of samples increase, our DFT starts approximating DTFT more and more. Okay? So this is where we had left off in the last class, and we'll move forward from here. So let's take a little example to make this point clearer. Let's say that we are given x of n equal to 1 for n from 0, 1 up to 4. So my xn is simply all ones, 0, 1, 2, 3, and 4, and it's 0 otherwise. But for the purpose of discrete time processing, I'm going to treat it as a length 5 signal. So it's a length 5 signal. Okay. Now I can compute its DFT using the DFT formula. You can do that. Right now we would not explicitly do that. We'll rather try to recover the DFT using its interpretation of samples of DTFT. So let's compute the DTFT of this. So the DTFT of this is simply n from 0 to 4 e to the minus j omega n, which is equal to, for little omega not equal to 0, that is equal to 1 minus e to the minus j omega over 5 over 1 minus e to the minus j omega. So I'm just using the geometric sum formula. It's my r is e to the minus j omega. I have 5 terms, so I get 1 minus r to the number of terms divided by 1 minus r. Okay? And if you manipulate it, you use the Euler's identity, what you get is 5 by 2 omega, sine 5 by 2 omega over sine of omega by 2. And there is the e to the minus j omega 5 by 2. So this is something that you have seen before. You have a signal which is nothing but a box signal. Now the DTFT of a box signal, it is this sine over sine form. So this is what we recover. It's, of course, it cannot be synced because DTFT is periodic. So it has to be sine over sine, which is periodic. And this e to the minus j omega 5 by 2, this is the phase shift that comes because our signal has been shifted to, it starts at 0. So because of this time shift, we have this phase shift, right? So remember, shift in time gives us phase shift in frequency. So I can plot the absolute value of this from 0 to, I'm going to plot it from minus pi to pi, which is our usual thing that we do. And what we see is that it is going to have 2 zeros between this. This is what it will look like. Yeah. It's supposed to be symmetric. The height of this at little omega equal to 0 is 5. And then it has zeros at little omega equal to 2 pi by 5. And then little omega equal to 4 pi by 5. I think I have an additional 0. This should be like this. And similarly, I have 0 at little omega equal to minus 2 pi by 5 and a 0 at little omega equal to minus 4 pi by 5. Right? So this is the absolute value. Now, as I said, you could have computed the DFT of this thing explicitly using the DFT formula, and you can do that. But right now, we want to interpret the DFT as samples of the DTFT. So let's ask ourselves, we just said that what is x of 0, the zeroth coefficient of my DFT? Well, from definition, that is equal to x of e to the j omega at little omega equal to 2 pi 0 over n. Now, what n do we want to use? Right? What point DFT are we talking about? So the first case, we say pick capital N equal to 5. Okay, the same as the length of the signal. So of course the x0 doesn't matter, but I just want to fix that at the start. So we get this is equal to 0. So x of 0, that means, is equal to x of e to the j0. And so absolute value of x of 0 is also absolute value of x e to the j0. So what does that mean? What is x of 0? That is the sample of this DTFT. So this is my x of e to the j omega absolute value. The zeroth coefficient is just the sample at little omega equal to 0. Okay, this is what my x of 0 is. So x of 0 is simply absolute value equals to 5. Okay, you could introduce the phase shift 2 and write the explicit value, but I right now don't want to do that. So now let's look at x of 1. X of 1, by definition, that is simply equal to x of e to the j omega at little omega equal to 2 pi by 5. So this means that x of 1 absolute value is absolute value of x of e to the j 2 pi by 5. Absolute value. So x of 1 is the sample of DFT at omega equal to 2 pi by 5. So this is my x of 1. So this is my x of 0. And this is my x of 1. Okay. So what is then my x of 1? That is simply equal to 0. Let's do that further. Say x of 2, that is equal to x of e to the j omega at omega equal to 2 pi times 2 over 5. So that means that x of 2, the second sample of my DFT, equals x of e to the j 4 pi by 5. So now I'm sampling my DFT at this location, and this is my x of 2. So I get 0 again. Now things get a little interesting because I have now x of 3, and x of 3 is defined as x of e to the j omega little omega equal to 6 pi by 5. Okay. So what do I do with that? I have x of 3 absolute value, that is equal to x of e to the j 6 pi by 5. But when I look at this plot, I don't have 6 pi by 5 in this plot because 6 pi by 5 is bigger than pi. So what do I have to do now? So to compute this x of 3, what I should do is, since I know that this value 6 pi by 5 is bigger than pi, what I need to do is actually extend this plot of my DTFT to up to 2 pi region. And how do I extend it to 2 pi region? I know that DTFT is periodic, so what comes after this is simply a replica of whatever I have from minus pi to 0. So what I get is this, and this will hit up to 5. Okay. So this is my replica of pi or from pi to 2 pi is the same as whatever is between minus pi to 0. And what will be this point? This point is going to be 6 pi by 5, and this point is going to be 8 pi by 5. Right? So now I can easily see that x of e to the j 6 pi by 5 is also 0. Okay? Which is the same as x of e to the j minus 4 pi over 5. I can also now ask what is x of 4. So x of 4 is simply equal to x of e to the j omega for little omega equals to 8 pi by 5. This means that absolute value of x of 4 equals to 0 again, because that is simply also sampling at this point. Okay. So that is the distinction that you have to keep in mind when you are sampling the DTFT, because we are used to seeing DTFT between minus pi and pi. But DFT samples the DTFT from 0 to 2 pi. So what we really need to now start doing is start learning not only plotting DTFT from minus pi to pi, but also extending it to 2 pi so that we can compute the samples correctly. Or if you don't want to, then you wrap those values around. You say 6 pi by 5 is nothing but minus 4 pi over 5. And then you write the value that way. Okay. So let's briefly verify that this is indeed what we would have gotten if we had used the DTFT formula explicitly. So what is the definition of DTFT? It is x of k n from 0 to 4 x of n e to the minus j 2 pi over 5 kn. Right? Our xn was all 1, so we get n equal to 0 to 4 e to the minus j 2 pi k over capital N times n. So capital N is 5. Now, we did this trick earlier for k equal to 0. This sum can be just computed because each term in the sum is just 1. So for k equal to 0, x of 0 is just summation of 1. So you have 5 ones, you get 5. And for other x of k, we can simply use, for k not equal to 0, we can simply use the geometric sum form. My r in this case is e to the minus j 2 pi by 5k. Right? So I get 1 minus e to the minus j 2 pi over 5k times 5, because I have a total of 5 terms, 1 minus e to the minus j 2 pi over 5k. Right? And the numerator is just 1 minus e to the minus j 2 pi times an integer. So e to the minus j 2 pi k is always equal to 1. You can use the Euler's identity to see that, and because of that reason, x of k is always equal to 0 for all k not equal to 0. Okay? So indeed, if I had just used the DFT formula, I would have gotten x of k equal to 5 for k equal to 0, and 0 for k equal to 1, 2, 3, and 4. So it matches what we had derived earlier. If you go back and look at our plot, we had x0 was equal to 5, and then all the others were 0. Right? So this is just to verify that indeed both the things will give you the same expression, but we want to sort of go back to the point that DFT helps you learn something about the DTFT. So I'm going to stick with the same example and just remind you that this is what our DTFT looked like. So from minus pi to pi. Okay. And we said we can extend that too. So this is up to 2 pi. This is what my DTFT looked like, or at least the absolute value. And when we computed our DFT looked like this. It is 5 for k equal to 0, and then it is 0 for k equal to 1, 2, 3, and 4. So k equal to 1, k equal to 0, k equal to 2, k equal to 3, k equal to 4. This is my x of k. Now, if you look at this stem plot, this stem plot doesn't look anything like your DTFT. Okay. The sampling relationship that we derived still is true, but the reason it doesn't look like your DTFT is because the samples that you are acquiring always landed on the locations where your DTFT was 0. Our second sample landed here. The next sample landed at this 0, the next sample landed at this 0, and then the next sample landed at this 0. So these were the samples that we had gotten. Now, how can we do that? How can we sample our DTFT better? We talked about it earlier. The way to do that is basically increasing the number of points of your DFT. The more points of your DFT you have, the more finally you are sampling your DTFT. So if we say that now instead compute a 10-point DFT of x of n, what does that mean? That means that x of k is from k equal to 0 up to 9, and each x of k sample, x of k is now equal to x of e to the j omega, with little omega equal to 2 pi k over 10. Okay. So now you are finally dividing. Previously you were taking samples every 2 pi over 5. Now you are taking samples every 2 pi over 10 radians. So if you did that, what would you get? Of course, at little omega equal to 0 or k equal to 0, you will still get the same sample, right? You will still get this sample. Remember, this point is 2 pi over 5, and this is 0. But what will be now in the 10-point DFT? What is x of 1? X of 1 is x of e to the j omega at little omega equal to 2 pi by 10. So you will obtain a sample at little omega equal to 2 pi over 10, which is between 0 and 2 pi over 5. So you'll get a sample here. Okay. The third sample will be still at 2 pi over 5, but the fourth sample will be here. Okay. It will be 2 pi over 5 plus 2 pi over 10. The next sample will again be at 4 pi over 5. So this point is 6 pi over 10, and this point is 8 pi over 10, which is equal to 5 pi by 4. Okay. And then what is the next sample that you will get? You will get a next sample at this location, at pi. Right? This point is little omega equal to 10 pi by 10. And then the next sample will be 0, the next sample will be here, the next sample will be 0, and then the next sample will be here. Okay. So now when you take your DFT, you are basically since you just double the number of samples, you are taking one additional sample between the two samples that you were taking before, and your DFT, absolute value of DFT will look like the following. You still have 5 at k equal to 0, but then you have now this value, then you get a 0 at k equal to 3, at k equal to 2, then you have another value, another 0, another value, another 0, another non-zero value, a 0, and then another non-zero value. Okay. So this is k equal to 1, 2, 3, 4, 5, 6, 7, 8, and 9. Okay. And the k equal to 5 sample corresponds to little omega equal to 5. So now it is starting to look more like, if you were to think of it, now it is starting to look more like the Fourier transform that you had previously. Right? If you draw an envelope, you can see sort of that pattern of this sink-like shape. So because of the periodicity of the DTFT, actually you can get to the conclusion that DFT itself is a periodic sequence, even though we always calculate DFT for x of k equal to 0, 1 up to n minus 1. If you ever were to say input a k different than these values, your answer will be actually k mod capital N. Okay, so what is this thing? This is defined as k mod n. It is the k mod n is the largest integer such that, so it's basically the remainder, the positive remainder that you get. Okay, so it's the largest positive integer such that k equals to q times n plus r. Okay, so this is your k mod n. So effectively, if k is positive, then this means that you simply look at remainder of k over n. Okay, and if k is negative, then you look at n minus remainder of k over n. So you can play with these expressions later, but the meaning is that if you had x minus 1, that is equal to x of n minus 1. Okay, and if you had like x of n, that is the same as x of 0. It's the periodicity. So going back to our discussion, what we have learned is that as we take more samples of the DTFT, and how do we take more samples? That is equivalent to saying that we compute DFT with a larger n, okay, i.e. compute DFT with more or with larger capital N, then our sequence starts to look more and more like our DTFT, but with the caveat that it is from 0 to 2 pi. So then our sequence starts looking like the DFT, the DTFT, but for omega equal to 0 to omega equal to 2 pi. Okay. So in the previous example that I showed you, if you were to use MATLAB and use FFT, for example, to compute the DFT of the 5 length 5 sequence, but you computed 10-point DFT. This is the plot you will get, okay? At least in the absolute value. Now, if we really want to think about computing or learning about the DTFT of sequences, we are used to looking at DTFT from -pi to pi. So what do we have to do if we really want to look at, okay, what does this DTFT look like from -pi to pi? We have to, in this case, we have to take these samples and put them in this half, okay? Because all of these samples correspond to, so this is up to this point is pi. All of these samples are above pi. And those samples are the same as the ones that you would have gotten from -pi to 0. So what you want to do is really shift these samples on the left side and then plot them so that you get a nicer view of what the DTFT would look like. You really want a sequence like it is, looks like the following. You want a sequence like this, okay? Whereas you are getting a sequence like this. The reason you want a sequence like this is because then you know that your DFT sort of looks like this shape, the DTFT, sorry. Okay, so we want a visual representation like the following. Or effectively what we want is we want to shift all samples of DFT or all coefficients of DFT from n plus 1 divided by 2, the ceiling of that, to n minus 1 samples to the left of the 0th sample. Okay. Why n plus 1 divided by 2? Because my n plus 1 divided by 2 sample, this is the ceiling operation, right? The largest integer bigger than n plus 1 divided by 2. So this definition means the largest integer greater than or equal to n plus 1 divided by 2. So the n plus 1 divided by 2, that sample basically is sampling at x of e to the j omega at little omega equal to 2 pi over n times k is n plus 1 divided by 2. Right? If you do that, then this will be bigger than pi. So the sample of my DFT at n plus 1 divided by 2, ceiling of that, is always bigger than pi, and so we want to move those samples, all of the samples, including that sample, till n minus 1 to the left, so that we can get a nice picture. Okay? And in MATLAB, you don't have to do it yourself. In MATLAB, there is a function called FFT shift, which does this for you. Okay? So if you basically compute the DFT using MATLAB FFT operation, you get a stem plot like the following, the one in red here. But if you take that sequence and you say FFT shift, MATLAB automatically knows that what you mean is you want to take the samples that correspond to little omega bigger than pi, and you want to put them on the left side so that you can think of it as a plot of samples from -pi to pi. So For that, you can simply say FFT shift of the sequence, and it will do this for you, and then you will get a stem plot that looks like the black region, the black stem plot that you see on the screen. So up to this point, we have understood the relationship between the DFT and the DTFT in terms of sampling. We said that if we just move things around, we look at a nicer stem plot. But what we really want to talk about is that DFT can be used to analyze the frequency content of continuous time signals. And for that, we need to actually be able to translate the DFT samples to the continuous time frequencies. So that part is called spectral analysis, which we are going to talk about not in too much detail. There are too many caveats involved in that, but in general, the spectral analysis for the sake of our class means using the DFT to infer about frequencies present in a continuous time signal. Spectral analysis is effectively, an example will be, let's say you are interested in finding out how many Wi-Fi signals are present, or what are the different bands of the Wi-Fi that different routers are using. So that's a continuous time phenomenon. Your routers are transmitting these RF waveforms which are living in certain frequencies. How do you evaluate that? Well, you don't have a continuous time processing system. So what you can do is you collect these RF signals which are continuous time, you sample them appropriately, and you do some sort of DFT analysis to be able to say something about these continuous world signals. Or another example could be you record my speech, you are interested in figuring out my voice has which frequency components present in it. How do you really do that? Well, you can't evaluate my continuous time voice, so you have to sample it, and then you have to do DFT analysis. So far we have talked about relationship of DFT to DTFT. We now want to take that relationship to DFT to the continuous time frequencies of your continuous time signal. Okay? So the way spectral analysis works is you are interested in analyzing the frequencies in some continuous time signal GA of t. And what do you then do if you are interested in doing that? You sample it at some time period t, and you get a sequence GN, and then you carry out the DFT of that GN to get the DFT coefficients GK. And then after that, you have some sort of visual analyzation or maybe computational analyzation to get back the desired outcome. One possible one is visual display. Okay. So if you ever go and work in, for example, a communications company which is interested in doing RF analysis, they own these very expensive spectrum analyzers, they are called. Okay? They collect, for example, they have these antenna that collect the signal, and then you have this display, very nice display, which shows you which frequencies are present. But the way they are doing that spectrum analysis is exactly this kind of a setup. Right? Your signal is picked up through the antenna, it's sampled, and then they do the DFT using FFT. It's very fast. And then they basically just do shuffling of the DFT in the right fashion. They know what the DFT sequence value means in terms of the continuous frequency. So you get a plot in hertz, but in reality, the operation is being done using DFT. So in this discussion, we are going to try to understand some of the details of that. How do you really map your DFT coefficients to continuous frequencies? So let's begin by asking, if we want to do spectral analysis and we have this kind of a setup, what are some of the key assumptions that we need to make? So what's the first assumption? If someone shows you this setup, what's the first assumption that you need to make? So the two key assumptions before you do any spectral analysis, the two key assumptions you have to make are about the band limited nature of your signal. The first thing is GA of T is band limited to certain maximum frequency. And if it is not, then what would you do? You would basically anti-alias filter it, low pass filter it, so that it keeps only the frequencies that you are interested in and throws away all the rest. And the other thing is that T is such that the Nyquist criterion is satisfied. Okay. So if these two assumptions hold, then we know that you will get a sequence which will have no aliasing. So what is spectral analysis about? Spectral analysis is about connecting G of K, the DFT coefficients, to the Fourier transform of GA of T. So to GA of J omega. Okay. Now, whenever you are given a block diagram, the way to do that is do it in steps. So to connect GK to the continuous time signal, what we want to do is first connect GK to GN in terms of frequencies. Well, we already did that. We already know that the DFT is nothing but samples of the DTFT. And the next thing you need to do is connect the GN to GA of T. That we have done it in previous classes. We know the relationship between the discrete time Fourier transform of the sample of a signal and the continuous time Fourier transform. So to connect GK to GA of J omega, all we have to do is connect these two blocks together. So the first thing is, what is the relation between GE of J omega, because we are all talking about frequencies, and GA of J omega? If we satisfy the Nyquist criterion, if GA of J omega is band limited, we know that from previous classes that we get three key aspects. One is there is a scaling of the amplitude. The other is we get repeated copies. And the third is we get a scaling of the frequency axis. So this is the relationship that we know. And from the previous discussion, we also know that GK is related to GE of J omega. How? GK is nothing but GE of J omega with little omega equal to 2 pi K over N. Okay. So that brings us to a caveat that I said we won't go into too much detail. What is that caveat? What is the main condition that you need to compute DFT? So to compute DFT, we need Gn to be finite length. And then not only finite length, but also What is the other condition? N has to be bigger than or equal to length of my sequence. So length of Gn. Okay. So while DTFT is defined for all kinds of sequences, the DFT is not defined for all sequences. And in many cases, then what happens is that we have to limit the sequence to a certain finite length. For example, if you generated a pure cosine, the only way you can really do an analysis of cosine is if you are given cosine from minus infinity to infinity. But we can't have a sequence from minus infinity to infinity, so we have to limit it to certain range. And when we limit our sequence to certain range, take the example of the spectrum analyzer, eventually you have to say, I have collected enough samples, I'm going to stop collecting samples and do FFT on those samples. That is a process called windowing. We are going to limit our sequence. That creates some imperfections. It's called leakage, spectral leakage. You get frequencies where they are not present. And the frequencies where they are present, they sort of lose their sharpness. We won't go into the details. I just want to bring that to your attention. You should be aware of those concepts. And we'll right now assume that that does not bring any imperfections. Okay, so we are going to assume without any loss of generality that when we limit Gn to a finite length, the length is so large that there is no imperfection. And we'll go from there. So we now know the relationship between the DTFT and the CTFT through this. Let's call this star. And we know the relationship between the DFT and the DTFT. Let's call that double star. So if we now want to say, what does a sample of my DFT tell me about the continuous time Fourier transform, I just relate star to double star. Okay. So let's do that. And we'll talk about now, we'll divide things into two pieces. So the first piece is for 0 less than or equal to k less than or equal to n by 2. This is the floor operation. Right? What does that mean? This means that little omega, which is defined as 2 pi k over n, right? This will be between 0 and pi. So if I give you the DTFT, you can tell me what is the continuous time Fourier transform by simply doing rescaling of the x-axis between minus pi and pi and rescaling of the amplitude, right? If I tell you what is GE of j omega between minus pi to pi, this means you know about GA of j omega from minus pi by t to pi by t is known. How do you do that? You simply scale GE of j omega by t and you scale the frequency axis. So since G of k for this range is for GE of j omega between 0 and pi, that is simply equal to GE of j omega at little omega equal to 2 pi k over n. I can just replace that. That is equal to 1 over t GA of j little omega over t, which is little omega equal to 2 pi k over n, which is equal to 1 over t. If I just plug in the value, I get GA of j 2 pi k over n t. Okay? So effectively, the kth sample of my DFT, as long as k is between 0 and the ceiling of n by 2, the kth sample of my DFT is nothing but a sample of my continuous Fourier transform, but now the sample location is determined by not only k and n, but also by your sampling period. Okay, it's determined by gk is given by 1 over t ga of j little omega, with little omega given by 2 pi k over n t. So basically what you can do is you can compute, if I multiply my gk with t, you can say that that is equal to what my frequency was at little omega, at capital omega, equal to 2 pi k over nt. Okay, it's effectively now, if you do these steps right, if your DTFT, let's say your DTFT was like this. Okay. This is minus pi over t. This is pi over t. What this relationship is saying is that your kth sample of your DFT from 0 to n by 2 ceiling or floor operation is like sampling the 0 to pi by t at every 2 pi over nt hertz, radians per second. Okay, so the gap between two samples is is 2 pi over nt radians per second, or in hertz it is 1 over nt hertz gap between samples. Okay. So this is your GA of j omega. And not only that, but you also have to keep this capital T scaling in mind. Okay, so there is also an amplitude scaling. But that is true from 0 to pi over t. What do you do from minus pi over t to 0? For that, you have to keep this relationship in mind, that as k goes above n by 2, you are actually sampling the DTFT from pi to 2 pi. But there is no relationship between continuous time Fourier transform and discrete time Fourier transform from pi to 2 pi. The relationship is from minus pi to 0. So you have to do that kind of FFT shift that we talked about. And so for the case when this is not true, when k is bigger than or equal to n plus 1 over 2, this ceiling operation, in that case the relationship between gk and the continuous time Fourier transform has to be changed. So in that case, we know that gk is equal to ge of j omega, little omega equal to 2 pi k over n, but that is also equal to, because of the periodicity of the DTFT, little omega equal to 2 pi n minus k over n. Okay. Now, if you do that, then you will see that 2 pi n minus k over n, the range of this is between minus pi and 0. So now you can safely relate the continuous time Fourier transform to the discrete time Fourier transform. So in this range, we can just plug in the formula for the DTFT and CTFT relationship. So our gk is ge to the j omega, little omega equal to 2 pi n minus k over n, but that is equal to 1 over t ga of j omega over t, 2 pi n minus k over n. This means that gk is equal to 1 over t ga of j 2 pi n minus k over nt. Okay. This is the relationship when k is greater than or equal to n plus 1 divided by 2 ceiling. So, or effectively you can say that GA of J 2 pi n minus k over nt is equal to T times GK. So the way then spectral analysis works is you compute your DFT coefficients, you do your FFT shift so that you move your DFT coefficients from minus, you move your DFT coefficients that correspond to omega equal to pi to 2 pi so that they go to minus pi to 0. And then you simply relabel the x-axis. You know the relationship between the different coefficients and their continuous time frequencies, and you also scale the amplitude. Okay. So if you are given, for example, if I take this example of, let's say my g of k was given like this. So if my g of k was given like the following, going back to the example that we had done earlier, okay. So it corresponded to a DTFT like this. This was my omega equal to pi point. So this is k equal to 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. The first thing you do is move these indices for k greater than or equal to n plus 1 by 2. Right? In this case, n was equal to 10. I move these here in this region. So I get a new formulation which looks, a new sequence which looks like this. Zero here. And so I get now this stem plot once I move things. So this is k equal to 0, 1, 2, 3, 4, 5. And this effectively was k equal to 9. Okay. And this is k equal to 8. This is k equal to 7. And this is k equal to 6. So I go up to this point. Once I do this shifting using the FFT shift, I then basically relate each of these points to a frequency. So for these indices, the frequencies, the continuous time frequencies that I get are given by 2 pi k over nt. Okay? So whatever is your n and whatever is your t, you can say that this is what the continuous time frequency was. Whereas for regions here, my frequencies are omega k equal to 2 pi over n minus k over nt. So that is the first step. You are doing the matching of the indices to the continuous time frequencies. And then for amplitude, whatever is the amplitude, so you had an amplitude of 5, you multiply that with your sampling period t. So each of these amplitude gets multiplied with t. Okay, that is due to the scaling that happens when you go from continuous time to discrete time. Okay. So spectral analysis is pretty much about you do the DFT and then it's really asking you how do you interpret these sequences that you have gotten, and the way you interpret them is through relabeling of the x-axis by doing a function of n and t, and also relabeling of the y-axis or rescaling of the y-axis through multiplication with t. And then whatever plot you look at, you say that is a surrogate for my continuous time Fourier transform of the signal. There are some imperfections involved, as I said earlier, because of the fact that you are limiting your sequence to a finite duration. So you get, because of the limiting of Gn, we get what's called spectral leakage, which means that whatever the plot we take a look at is not really the exact plot of the reality, but it's we try to make it as close as we can. Okay. Now, I want to just finish with one thing, that in spectral analysis, so DFT in the spectral analysis world basically is sampling your continuous time Fourier transform every 2 pi over nt radians per second gives you a new sample. Okay. So this 2 pi over nt in the world of spectral analysis is called spectral resolution. It means that what is the gap between two samples of your continuous time Fourier transform. And if you have things that are happening at a very fine frequency scale, then you want the spectral resolution to be really a small number. Okay, so how do you determine that? Or you can also say it's 1 over nt hertz. So say someone says that I want you to tell me what is happening in the frequency domain where the frequency samples are no more than 5 hertz apart. Okay, so we want to know what is happening every 5 hertz, and the sampling is fixed at 1 over 8,000. So you are sampling at 8 kilohertz. So then what is the parameter that determines your spectral resolution? The parameter is n. Okay, how many points of DFT you need to take? So what we are saying is we want 1 over nt to be less than or equal to 5. This means that n has to be bigger than or equal to 1 over 5t. This means that 8,000 divided by 5, 1,600. Okay, so if you want to do spectral analysis where you are sampling every 5 hertz at least, then when you get to the DFT stage of your spectral analysis, you better make sure that your DFT is computed at least for n equal to 1,600. And of course, the other thing you have to keep in mind is if you are computing DFT for n equal to 1,600, then your sequence must have length smaller than 1,600. So if that is not the case, then you end up with this issue of spectral leakage. And the last point is that the spectral leakage concept, which I am just being vague about, cannot be improved by taking more samples of your DFT. Okay. So I'll conclude here.